the last video, if you recall, we talked about the Fourier series representation for an extremely broad class of signals that are periodic in nature. So we represented a periodic signal, xt for example. If it is periodic, then you recall that xt can be written as such that if it is periodic, then there should be a period, a non-negative and a positive quantity. It should exist such that the following relation is satisfied. So xt plus capital T should exist, which satisfies the relationship. Okay, there should be a capital T which happens to be the period, and it's a non-negative positive quantity. Okay, which is the fundamental period of the signal xt. So if that is the case, then the series on the right hand side also has a period of capital T. Okay, which means that it is representing the signal xt as a linear combination of exponentials. Okay, you see the series is a linear combination, weighted and linear combination of complex exponentials. So now, how good is this approximation? How good does this series approximate a periodic signal xt, or what are the conditions that the series converges? Will be the discussion in upcoming videos. Okay, so we're not going to talk about that right now, but just to give you some insight into this, Fourier series is a very good representation of extremely broad class of periodic signals, but it's not an exact representation of signals which are, for example, discontinuous, okay, or which have some singularities. You'll see that later on that there exists a very common phenomenon known as Gibbs phenomena. Okay, even if you include large number of harmonics in Fourier series expansion to approximate a periodic signal with a jump discontinuity, there occurs peaks and dips around that discontinuity, where the discontinuity occurs in the function. Okay, so it's not an exact representation of periodic signal, but yet a very good representation of a very broad class of signals yet. So what we're going to do now is that we are interested in determining these spectral or Fourier coefficients given by AK. Okay, and so what we are going to do is to determine. We are going to determine the determination of the Fourier series representation of continuous time periodic signals. So if we believe that this Fourier series representation is representing your periodic signal xt, then we must find out these Fourier coefficients AK. So how to do that? Okay, so assuming that a given periodic signal can be represented with the Fourier series, we need a procedure for determining the coefficients AK. So multiplying. So how we do that is we start off with the same mathematical artifice that we multiply both sides of the series with e minus j and omega naught. Okay, assuming omega naught is the fundamental frequency of the signal xt, which is given as 2 pi by t. It's in radians per second. Okay, so again, you see that. Okay, if you multiply this with e minus j and omega naught on both sides, you see that you can combine this exponential on the right hand side of the equation into one exponential. Okay, so it can be written as such, and then you integrate your both sides of the equation over the time period interval of the signal xt. Okay, so integrating both sides from 0 to 2 pi by omega naught, that happens to be the periodic interval. So this integration mean is the area. It's not the area under the function for one period. It's the area under the function multiplied by e minus j and omega naught t. Okay, so this is the integrand. The integrand is not xt, it's e minus j and omega naught t. All right, and the same thing occurs on the right hand side. And now if you notice that the summation is over k. Okay, but the integration variable is t. They are independent operations, so the operations can be interchanged. So if you bring forward the integration, okay, so you have an exponential in the bracket. Okay, and if you look closely, this bracket can be expanded from Euler's identity into so integrand can be expanded into cosine and sine functions. Okay, over the same interval you can integrate cosine and sine functions. So over here, if you notice, omega naught is still your 2 pi by t, and what this expression is telling you is that this cosine and sine functions are periodic with period, let's say t1 equals to fraction of capital T. So it will be t by k minus n, okay? Because k is some integer, n is some other integer, then k minus n is also an integer, so it becomes a fraction of t, okay? So, but just remember that t is the fundamental period of xt, okay? So consequently, we are integrating over one period, right? But interchanging the order of integration and summation, okay, what we've done over here, the evaluation of the bracketed integral is straightforward. So rewriting this integral in Euler's formula, we can write this as cosine and sine. But these expressions, they have their fundamental period is not t. It's a fraction of t by k minus n. Okay. So for k not equal to n, k is equal to n, then you can see that the integrand on the left hand side of the equation is 1. Okay. K equal to n means 0, and you're just integrating 1 over the interval 0 to t. So for k not equal to n, cosine k minus n omega naught t and sine k minus n omega naught t are periodic sinusoids with fundamental period t over k minus n. Therefore, we are integrating over an interval of length t. Okay. So you see, if you integrate this over the interval 0 to t, that means you're integrating it over, you're including in this interval many sine waves, okay, multiple sine waves, k minus n sine waves, and the result is 0, right? So that is an integral number of periods of the signal. Okay, for example, if you are going to integrate, for example, sine function over one period, the result is 0, right? I mean, whatever is the area on the positive axis, then you have the same area against the negative axis, and those areas, they cancel out. Okay, so over one period, this the integration over one period of sinusoids is 0. So even if you're going to integrate this over multiple, you're going to include multiple intervals, okay, multiple period intervals, even then the result is 0. Okay, so since the integral may be viewed as measuring the total area under the functions over the interval, we see that for k not equal to n, both of the integrals on the right hand side are 0. So both of these integrals for this interval 0 to t are 0. For k not equal to n, this is 0, this is 0. Okay, and let me indicate this, that this is 0 for k not equal to n. Okay, well, what happens when k is equal to n? When k equal to n, you can see on the left hand side, the integrand becomes equal to 1. This is 1 for k equal to n, right? That means the left hand side simply becomes capital T, right? So basically, the result of this integration is capital T for k equal to n. Okay, for k equal to n, and for k not equal to n, so for k not equal to n, this integration is 0. So in the brackets, the result will be 0 if k is not equal to n. So in the brackets, the result is k is equal to 0. For k not equal to n, sorry, this is not 0. This is for k not equal to n, the result is 0. Okay. And if you recall, what we are doing again is we are once we okay, now since we have started to believe that, okay, there is a Fourier series which is an alternate representation of the periodic signal xt and has the same period capital T, and this series happens to be the expansion of complex exponentials, weighted complex exponentials. We are now interested in finding how to find the weights, or if you so want to call them, the Fourier coefficients, aka the Fourier coefficients. Okay, so how to find them? We have just started with the multiplying. We did some algebra. So we multiplied both sides with e minus j omega naught t, and then we are looking at we are integrating the both right hand side and left hand side of the equations or one period. We are integrating this over an interval of one period, and then for these dummy variables k and n, for k equal to n, we find that this bracketed integral is capital T. For k not equal to n, this is 0. So so now you see, for k equal to n, the integrand on the left hand side equals to 1, thus the integral equals to t. So if you use this definition, I mean, if you use the result of this integration, you can find the Fourier coefficients very easily. Okay, you can just bring t on the left hand side of the equation, And you can see that the Fourier coefficients are nothing but ak is equal to the same integration 0 to capital T xt minus j omega t. 1 over t is going to come over here. That's it. This is your these are the Fourier coefficients. Okay, for k equal to n. Okay, so in sum, what we have now is that using this result of the integration, on the right hand side of the following equation reduces to the right hand side. Okay, the right hand side is now basically it's the entire result is equal to t. So this is t multiplied by ak. Okay, so this is tan. Therefore, you have the Fourier coefficients as n equal to 1 over t xt minus j omega naught t. Okay, so these are the Fourier coefficients we are interested in. What do they represent? Well, let's go back to the series, and they represent the strengths of the corresponding harmonics that are present in the original periodic signal xt. Okay, so ak are the Fourier coefficients, or you can say these are the spectral components, just like a light can be decomposed into its spectral components. In a very similar manner, ak happens to be such Fourier coefficients or spectral components that reflect the power in each harmonic. Okay, for example, omega naught is the fundamental, then that's for k equal to 1, and then for k equal to 2, its second harmonic, k equal to 3, its third harmonic, and similar with that, A2 and A3 are representing the strength of the harmonics, how much portion of that harmonic is present in xt. Okay, that's what is being represented. And AK or AN is represented by, since k equal to n, since k is equal to n, so either AK or AN doesn't matter. N equal to 1 over t, 0 to t, xt e minus j omega naught t. So you notice that over here, it's not the average of the signal. Okay, it's there's a term e minus j omega naught t that has to be multiplied with xt and then integrated. And for particular n, you have to, for example, if you have to value it for a1, then this is e minus j omega naught t. For a2, it will be e minus j twice omega naught t. Okay. However, you can see from here, if you have to evaluate the DC term, if your signal consists of any DC term, well, then it's the average. You can say this is the average of the periodic signal xt. Okay, so over one period, let's say t, this becomes 1 over t xt dt, because n is 0. Okay, and this is for n equal to 0. This is exactly the average of the signal. The DC is exactly the average of the signal. So this happens to be the strength of that DC as well. And for n not equal to 0, you have the harmonics. Okay, starting with the fundamental. So you start measuring the strengths. That is the Fourier coefficients. Okay, so in evaluating the above integral, now if you recall, we expanded this in terms of cosine and sines. The only fact that we used concerning the interval of the integration was that we were integrating over an interval of length t, which is an integral number of periods. So cosine k minus n omega naught t and sine k minus n omega naught t. Therefore, we'll obtain the same result if we integrate over any interval of length capital T, right? Because you see, again, over here, your time period was the fraction of the original time period capital T by, so it was T by K minus n. It was a fraction of capital T. So we were integrating over 0 to T, so there is no loss of generality. I mean, you can consider the period 0 to twice T or 0 to 3T. I mean, if I consider this period 0 to 2T or 3T, this equality holds, and the results will be very similar. Okay, the results will be alike. So, I mean, even if you are going to consider again for k not equal to n, for even for k not equal to n, then this will be 0. Okay, since for k not equal to n and you are integrating over, you're including more cycles. Okay, the result is still going to be 0 for both the integrals. Okay, for both sine and cosine integrals. So for k not equal to n, it's still 0, and it will be t for k equal to n. So in general, the definition of the Fourier coefficients, I mean, it's the same. So therefore, we will obtain the same result if we integrate over an interval of length t. So that is, if we denote the integration over an interval of length t, then by you can write this as 1 over t integral. This is one time period, for example, xt minus j omega naught t. So okay, so this is the definition of the Fourier coefficients. Okay. Now to summarize, if xt has a Fourier series representation, so if you believe xt can be decomposed into complex exponentials with the respective weightages, aka Fourier coefficients, then if it can be expressed as a linear combination of harmonically related complex exponentials, then the coefficients ak are to be determined. So the following pair of equations then defines the Fourier series of a periodic continuous time signal. So if xt can be decomposed into complex exponentials with their corresponding Fourier coefficients, then AKs are given as such. Okay, so the first equation is the we say that this is the Fourier series. Okay, this is the synthesis equation. This is combining the exponentials with their weightings. You're synthesizing xt. Okay, and remember omega naught is basically 2 pi by t. Okay, omega naught is 2 pi by t over here. So you're synthesizing xt, and the second equation is the analysis. Okay, so here we have written equivalent expressions for the Fourier series in terms of the fundamental frequency omega naught and the fundamental period t. The first equation above is referred to as the synthesis equation. Second is the analysis equation. Okay, so use the second analysis. Use the second equation to analyze or find the Fourier coefficients which are related to each harmonic. Okay, so the set of the coefficients are often called Fourier series coefficient or the spectral coefficient of xt. These complex coefficients, they measure the portion of the signal xt that is at each harmonic of the fundamental component. Okay, so the coefficient a naught then is the DC or constant component of xt, and it's given by the following equation. So for example, what if your signal is sine omega naught t? Okay, this is example 3.3, and if you have to determine this is a periodic signal. Okay, so you can see that the period capital T is given by 2 pi by omega naught over here, and if this is a periodic signal, then this should be expressible in terms of Fourier series. Okay, so it should be equal to you should be able to decompose this into complex exponentials. So it should be e j k omega naught, where k is the harmonic index t. Okay, so this is e j k omega naught t, and this summation has to be over k. So how many Fourier coefficients are representing? Well, one way to find that out is use the Fourier analysis equation. Okay, so the integrand will be looking more complex. I mean, you will have a sine term and then exponential. The easy way is to just expand the sign in terms of Euler identity, and then compare this with the Fourier series directly, and you will find out that your a1 is 1 over 2j. Okay, for k equal to 1, and for a minus 1 you have 1 minus 1 over 2j. Okay, I mean for k equal to 1, because this expansion, well, if you start with DC, okay, let's start with DC, a naught. So what happens to a naught? You see, sine intuitively has no DC component. The DC component is 0. DC component is 0. So sine doesn't have any DC component. Even if you go to find, you use this. Okay, if you put k equal to 0 and find the DC value, well, that is for sine, for a sine function, for a sinusoidal function, when xt is sinusoid, when x is a sinusoid function, then this result is basically 0. Okay, sinusoid means sine of cosine, 0. The DC is 0. So you don't have any a naught. You don't see any a naught in this expression in the Euler's decomposition. Then you will have the Fourier coefficient a1 e j omega naught t. Okay, and then you on the other side you will have a minus 1 e minus j omega naught t, and then you can see that there is no point in expanding this for a2 and a3. I mean, you don't need to write this for k less than minus 2 or k greater than 2. I mean, you don't need to consider the harmonics beyond the fundamental, the second harmonic, the third harmonic, because you don't see it's not 2 omega t or it's not 3 omega t. There's nothing like that. So all these coefficients are zeros. Okay. Thereafter, all the coefficients after the fundamental, the Fourier coefficients are all 0. Okay. So if you compare this series expansion with this Euler decomposition, it's very easy to see the Fourier coefficient. Okay, it's very nicely, I mean, everything fits in very nicely. You just compare the Fourier series coefficients with the Euler expansion of sine, and you can find out what these coefficients are. And in fact, this well, sinusoid is, first of all, it's not a discontinuous function. It's just a periodic function with no discontinuity, and it can be expressed by Euler's in terms of exponential. And if you compare this with the Fourier series, well, Fourier series is very easily, you can express sine in terms. You can basically decompose naturally. You can decompose sine and cosine into exponentials, and therefore you can write this in terms of the Fourier series. So Fourier series is exactly representing the sine over here, okay, where the coefficients of a1 and a minus 1 are 1 over 2j and minus 1 over 2j, okay. However, the DC term a0 is 0, okay. You must understand the DC term is 0. Its average is 0 of sine and cosine. Okay, so you see, one approach was to determine this Fourier series coefficient of this signal is to apply Fourier series analysis equation, but this was a little bit cumbersome, and we would have spent some more time in doing the integration. A better way, a simple case, was to expand the sinusoid as a linear combination of complex exponentials, identify the Fourier series coefficient by inspection, and just write the coefficient. Okay, let's take more involved example, which consists of a linear combination of sinusoids. Okay, so we have the first term. The first term is DC. Then we have a fundamental frequency omega naught. Then there's another sinusoid having frequency omega naught. The fourth term is consisting of a second harmonic of omega naught. So we have a linear combination of sinusoidal signals. And how, the question is, how can we represent this in terms of Fourier series? Okay, how can we express this as a linear combination of complex exponentials? And if we want to do that in terms of Fourier series, we want to decompose this into exponentials. Then what are their corresponding Fourier coefficients? What are the corresponding Fourier coefficients of all these harmonics? So again, if you want to compare this expansion with just writing sine and cosine in terms of their exponentials, so just you see, this is again sine, this is cosine, this is again cosine with the phases, okay, and you can basically you can extract two exponentials, okay. So again, you can see the second harmonic is there, first harmonic plus minus 1, and it's very easy to see from this term that this term, the first term of unity, refers to the DC component of the signal, that is A0. Okay, A0 is the DC Fourier coefficient. Then for k equal to 1, this term, if you compare this for k equal to 1 in the expression, this refers to A1. Okay, this is your A1, and this becomes the coefficient of for e minus j omega naught t, k equal to minus 1. This is for a minus 1. Okay, so for k equal to minus 1, so this is a minus 1. Similarly, it's very easy to see that we're just comparing this expansion. We are just comparing basically this expansion with the series, and we are trying to find the coefficients just by inspection. Okay, we are not integrating. We are not using any analysis equation. So it's quite straightforward to see that these coefficients are just right there, okay, in front of you. So if you compare this with this expansion, see the DC term is 1, then the first Fourier coefficient A1 is 1 plus 2j, then A minus 1 is 1 minus 2j, okay, 1 minus 2j, this is for k minus 1, this is for k equal to 1, this is for k equal to 1 over here, okay, for k equal to minus 1, this you're looking at over here, for k equal to 2, this is A2, and then for k equal to minus 2, this is here, okay, and ak is 0 for modulus k greater than equal to 2. What does this mean? This means that ak is 0 for k less than minus 2, and it is again 0 for k greater than equal to 2. Okay, oh, sorry, for k greater than 2. It's not 0 for k, it should be greater than. Okay. So, I mean, this example 3.4 is very similar to example 3.3, which are from your course text. So just by, I mean, even if you have a linear combination of sinusoids, they can be broken up into, they can be written into Euler's, they can be written up into, expressed in terms of exponentials, decomposed into exponentials. And then if you compare with the Fourier series expansion, by inspection, you can just find the Fourier coefficients. In a very straightforward manner, or directly. You don't need any Fourier analysis equation that we have seen over here, okay? But then it turns out that there are functions, other functions like square waves, okay, um, or square pulses separated by some interval, which are periodic or sawtooth waveforms, for which you have to use the Fourier analysis equations to determine the Fourier coefficients, okay? All right, so this is again exact representation of the periodic signals. And if you want to plot this magnitude of AK, so AK represents, so for example, DC is contributing a lot of power in this signal, okay? There was a DC itself, you see the DC was there. And then we had this, well, A1 contribution is coming from both the sinusoid, this is from sine, this is from cosine, okay? So from cosine, this is 1, over here, you see this 1. And then from sinusoid, this is 1 over 2 plus minus 1 over 2j. So A1 and A minus 1, the power being contributed by these two signals having fundamental frequency of omega naught is, you can see, much greater than, it's much greater than twice omega naught, because this is 2 over here as well. So if I have to consider this intuitively, then the fundamental frequency contribute more power. The Fourier coefficient strength is higher as compared to the second harmonic over here. Second harmonic has a lower strength, has a lower portion as compared to the fundamental, okay? And then there is a phase as well, okay? So A2, A minus 2, you see the phase is plus pi by 4 and minus pi by 4. Just look at the Fourier coefficient. We are plotting, over here you're plotting magnitude of AK and basically the phase of AK. And the phase of AK for minus 2, for example, for minus 2 it is minus pi by 4. 1 over 2 is going to contribute the phase of 0, okay? So for example, how do you write this as 1 over 2? E j pi by 4 is, well, you can decompose this. Phases are going to add, okay, for a complex quantity. So the phase of half is 0, okay, it's real, and plus phase of E j pi by 4 is itself pi by 4, okay, it's pi by 4. Basically it's pi by 4. And then for the this is for A2, okay, for A minus 2 it will be minus pi by 4. So there's going to be a phase reversal. So at minus 2 this is minus pi by 4, then at plus 2 it is pi by 4. It is quite evident from here, plus 2 it is plus pi by 4, minus 2 it is minus pi by 4. And I mean, since A1 is also complex, it's going to have phase, and due to this reversal of sign, the phases are going to be reversed. So this is the story at the fundamental, but the same phases, okay, even at the second harmonic you have the same phase, pi by 4, but the sign is different. The DC term is going to have 0 phase, okay. So these are the phases. The AKs are generally complex Fourier coefficients, and if you want to plot them, you want to have both the magnitude and the phase plot. This is the magnitude plot of the Fourier coefficients, and this is the phase plot of Fourier coefficients. So this is the plot of magnitude and phase of Fourier coefficient of signals. Consider an example 3.4. So basically what it says is that it represents the portion or the power of the signal which is forming up with how much power each harmonic is contributing into the signal is being represented by these graphs, okay. So for example, the fundamental components are contributing more power as compared to the second harmonic. There's only one term, there are two terms of the fundamental, so it's expected the fundamental is going to have more power than the second harmonic over here. This is the second harmonic, and this is the first harmonic. And DC term is the lone term, okay. Its magnitude is comparable to that of fundamental signals, okay. All right, now another example. It's not consisting of, it's not the sinusoid or linear combination of sine signals. It is a square waveform, okay. It's the periodic square wave. Sketched below and defined over one period is as such. So xt is 1, okay. It's a unity for t starting from minus t1 to plus t1, okay. It takes the value of 1, and it is 0 otherwise. I mean, in the interval, over interval of capital T, it is 0. So that means xt exists for a for a fractional period of capital T, okay. Capital T happens to be the fundamental period, but over T1, from minus T1 to plus T1, the signal is there, but then from t1 to capital T by 2 there is no signal, so it's like this, okay, and then this thing is repeating itself. So this is periodic signal. This is a periodic signal having a period capital T. So because of the symmetry of xt about t equal to 0, it is convenient to choose minus t by 2 to plus t by 2 as the interval over which the integration is performed for Fourier coefficient evaluation. So although n interval of length t is equally valid and thus will lead to the same results. Okay. All right. So the signal is periodic with fundamental period t. So this is also omega naught equal to in relation to the fundamental frequency is in terms of capital T is 2 pi by t. Okay. So let's recall the Fourier analysis equation that we've considered before. This time we are not going to we cannot compare the Fourier series with the sine expansion or cosine expansion. We have a square wave. It cannot be decomposed into exponentials in a straightforward manner. So we have to use this this equation over here, which is the Fourier analysis. Okay, and xt is the square wave. So we have to put this definition over here, and then have to integrate this to find the Fourier coefficients. Okay, so let's bring this equation over here. Fourier analysis equation is over here. So first, let's try to find what is the DC. So for DC, there is no e minus j k omega naught t, k is 0, right? So a naught is simply the DC or the average value of xt. So using the same limit of integration, you first look at k equal to 0, the DC coefficient. So as mentioned earlier, a naught is to be interpreted as the average value of xt, which is here as the case, but in this case is a fraction of each period during which xt equal to 1. So we are taking the average over here. So since xt is unity from minus t1 to plus t1, and you're just going to substitute this for the intervals, and you're going to find out that a naught happens to be the fraction of capital T, that is 2t1 over capital T. It's a DC term. Okay. Then for the other Fourier coefficients, when k is not equal to 0, we have the integrand is not xt but xt e to the minus jk omega naught t, and then you have to integrate this from minus t1 to positive t1 because that's where xt is unity. Okay, so there is one over here as well over this interval. If you do this integration, you can combine these two exponentials into a sinusoid. Okay, and then recording that omega naught t is nothing but is 2 pi. Okay, so this 2 cancels, so you're left with k pi over here. So these are the Fourier coefficients for k not equal to 0. For k equal to 0, this is the story. For k equal to 0, this is the average value of the signal. And for k not equal to 0, these are the Fourier coefficients that are representing the that are representing the strength of the harmonics, which are composing the signal xt. Okay, so for the specific example, the Fourier coefficients are real, and you can see from here. We combine the two exponentials into a sine form, so the Fourier coefficients are real, and consequently they can be depicted graphically with only a single graph. So we don't need the phase, just like we saw the phase over here in the last example 3.3, 3.4. We don't need phase. It's real, so only the magnitude graph is good enough to show the strengths of the harmonics. So more generally, of course, the Fourier coefficients are complex, so that two graphs corresponding to the real and imaginary parts or magnitude and phase of each coefficient would be required, but we require only one graph for this example. Now, let t be equal to 4t1. Okay, now what we are going to do is we are going to express t1 in terms of t. Okay, so for the first case, let's assume t equal to 4t1. Then if you substitute this over here, t is equal to 4t1, that means the DC coefficient becomes equal to 1/2. Okay, so DC coefficient becomes 1/2. So xt again is a square wave for this interval, that is its unity for half the period and 0 for the other half period. In this case, omega naught t1 in terms of capital T is pi by 4. Okay, so 2 pi over it's like because we are substituting this for, since t is 4t1, it's not 2 pi, it becomes pi by 4. Hence the Fourier coefficients become, well, this expression k pi by 2 is coming from here. So kt1 is kt1 is going to be So not kt1, the omega naught t1 is going to be pi by 4. So you can write this as sine k pi by 2 over k pi. Okay, and then you can see that for ak is equal to 0, ak, the Fourier coefficients are going to be 0 for k even and non-zero. Okay, if k is even, like 2 or 4 or 6, that means the Fourier coefficients are 0. That means the the periodic square waveform is not going to consist of even harmonics. It's going to consist of only the odd harmonics, that is omega naught, 3 omega naught, 5 omega naught, and so on and so forth. Okay. So also sine k pi by 2 alternates between plus minus 1 for successive odd values of k. Therefore, you will only find the odd harmonics a1, a3, a5 with decreasing magnitudes and alternate signs. Okay, this is also depicted over here in figure A. For example, figure A is t equal to 4t1, and you see that the maximum strength is 1 over 2. It's half, 0.5. Then 1 over pi is 1 over 3.142. Okay, so it's smaller than 0.5. So you see the strength is going to decrease. So then, for example, the third harmonic is 1 over 3 pi and then 1 over 5 pi. So there are no odd there are no even harmonics, but plus minus 2, which is 0. Plus 1 is 1 over pi. Okay, this is 1 over pi. This is 1 over pi. This is the first harmonic. Then the second harmonics are, you see, this is 1/3 is the power. Sorry, this is 1/5, not 1/3. We are looking at the fifth harmonic. Second, third, yeah. Over here, this is 1 over 3 pi. Third harmonic is 1 over 3 pi. Same power, 1 over 3 pi. So this power is decreasing. Okay, this power is decreasing. This is 1 over 5 pi. And then you will have 1 over 7 pi. Then for this 1 over 7 pi, well, this is 1 over 9 pi, and this continues. Okay. And in part B, we have t equal to 8t1. So again, the strengths are decreasing. The Fourier coefficients are decreasing in strength like this. So as you go on increasing this interval, when capital T is 16 times t1, the depiction is having the same morphology, but the spacing becomes more and more. Okay, so because the coefficients are regularly spaced samples of the envelope 2 pi sine t1 over omega, the spacing between the samples is decreasing as t is increasing. So as t is increasing in these figures, the spacing between the samples is decreasing. So for example, in these samples, the samples are coming more and more together. But again, you're not going to have any even harmonics. There will be odd harmonics. So for a sine wave decomposition, just remember that it doesn't consist of even harmonics. It has odd harmonics, and these odd harmonics, the strength of these odd harmonics is decreasing. Okay, third harmonic has a lower strength than the first harmonic, than the fundamental. Okay, then the fifth harmonic has a lower strength than the third harmonic. So fifth harmonic is not contributing as much power as the third harmonic is contributing. So odd harmonics are there, but the strengths are decreasing. Okay, so the fundamental has a maximum power, and then the strength decreases. Fundamental is 1 by 2 over here, and then the strengths are decreasing. So that is the story. Okay, that's how you use the Fourier analysis to find the coefficients, and then you can write this series in terms of complex exponential. You have to find AKs, and then you can represent a very broad class of periodic signals in terms of linear combination of complex exponentials with the corresponding ratings. Okay, that's all.